Good evening. I'm Hank Levy, and I'm chair of the Department of Computer Science and Engineering at the University of Washington. And it's my pleasure to introduce to you Professor Yoky Matsuoka. The research world is becoming increasingly interdisciplinary, and Yoky is a prime example. Her work moves from neurons to muscles to software to robots. Yoky was born in Japan and moved to the US at a young age. As an undergrad at Berkeley, she studied electrical engineering and computer science. But more important, she was named a Scholar Athlete of the Year for her tennis play. Yoky did her graduate work at MIT, where she received a PhD in 1998 for her work in artificial intelligence and neuroscience. Following postdocs at both Harvard and MIT in mechanical engineering and in brain and cognitive science, she joined Carnegie Mellon University in 2001, where she was a professor in the Robotics Institute in mechanical engineering and in the Center for the Neural Basis of Cognition. Luckily for us, Yoky decided to leave CMU in 2006 to join us in the Computer Science and Engineering Department at UW. And we're very happy that she did that. A little more than 1 year ago, Yoky received a life-changing phone call telling her that she was the recipient of a 2007 MacArthur Genius Award. And she's been on the road giving talks ever since. Finally, for those who want that personal interest tidbit, I can tell you that on top of all that she's accomplished, Yoky is the mother of adorable twin girls and a 1-year-old baby boy. She has a dog named Jalapeno, and as far as I can tell, she does not require sleep. With that, I'd like to turn it over to Yoky.
Wow, thank you very much. It's very, very exciting to be here. And thank you so much for coming at 7 o'clock on a weekend night. So hopefully I can be entertaining this evening. But it's really funny to start with the introduction about this Genius Award. So I always feel really embarrassed about it, even though I'm, of course, honored. I'm starting to experience this interesting life of being famous. And then one example of that was that about 3 months ago, I was sitting in the Seattle airport. And I usually I do all my business trips with my infant baby, who is still breastfed and so forth. So I was dressed like a mommy and trying to hide from everybody and holding my baby. And then suddenly 2 people over there staring at me, and I thought, oh boy, I must have something horrible on me. So I'm like checking and looking. And then one of the guys stood up and then came over to me and said, excuse me, are you the certified genius? So I said, yes, I guess so. And then he looks over to his buddy across and said, hey, dude, she's the one, she's the genius. So now like the whole airport is looking at me. And then that was really awkward, and then we got on a plane, put the seatbelt on, and took off. Seatbelt sign came up, ding, and people got up and got in a line to ask me questions. But you know, what's interesting, you know, I assumed, I had no idea what people were going to ask, but turned out that the kind of questions, or actually the majority of the questions were about, you know, I'm a father and I have an 8-year-old son, and I think he's a genius. And I like to get your advice on, you know, sort of how to make sure that he's really going to pursue the right path. Should he be taking the right math class, or should he be, you know, doing some accelerated school? And, you know, where is it? What is it? You know, let me write it down. And my answer to all of that was that, you know what? You know, don't push them in doing anything. And then if anything, sports and music. And that really, that sort of the fundamental idea of just pursuing something that really enjoy on the side, and maybe doing it too much, maybe, it's okay. I think that also teaches them a lesson, and that's where I really started. So, you know, that's my picture from college. I grew up playing tennis, and that's all I wanted to do. I played about 4 hours a day, 6 days a week, training, in addition to a variety of conditioning. That's what I did for all my teenage years. And it taught me a lot. It taught me endurance, competitions, and it was amazing. But when I was about 19, I came to realize that this is not going to be it. I was very injury prone. If you look carefully, I actually have a lot of things wrapped around my legs. And I was a basket case. So I was famous actually in a physical therapy room because of that. So that actually got me to think about what I had to do for the rest of my life. And I decided that science and math is kind of fun, and maybe I can do something with it, but still as part of tennis. So I decided that what I really wanted to pursue was to build myself a tennis buddy. And this tennis buddy would be made of robotic device and maybe some artificial tissues and so forth, and it would have knobs. And those knobs that I can tune, and on days that I'm tired, maybe I can tune it a little bit weaker. And on the days that I want to be challenged, it will make it just a little bit better than me. And not only just the speed of the ball, but just strategies and intelligence and all of that, and run around on 2 legs and so forth. So I even went to college and asked the professor. I just knocked on the door and said, hi, I used to be a tennis player. Now I'm going to go and do engineering, and I really want to build my tennis buddy. And some professors laughed at me, and some actually took me on. And then I got to do some research in legged robotics as an undergrad. And I went on to MIT and then kept pursuing the same dream. This is a robot called COG. The COG is a torso-up robot supposed to achieve about a 2-year-old intelligence using 5 years of graduate student time. And we didn't come too close, but we've certainly tried. And I was in charge of the upper limbs, arms and hands. And I built the hand on the right-hand side. And this hand was built with babies' capabilities. Babies, when they're born, they already have reflex. You touch their hand and they curl around your fingers. And then you tickle the outside and they open it. That's what I hardwired in software. And everything else was in neural networks. It learned everything else given the motivation of the robotic device. So I walked around of this hand. The robot didn't have legs. I put it on a stick. And I walked around with this hand in the lab. And then I just let it experiment around with different inputs from the hand. And it grabbed and tried. And over trial and error, it learned to grab most of the objects that was light enough in the lab. And I thought, wow, this is really great. This is like a little baby. But then I started to think that, well, OK, I could grab a lot of things, but I do more than grabbing things with my hands. I do all dexterous things. Maybe I can actually sort of turn this around in my hand. And I tried to program that in systems like this, and I just could not achieve it. And at that point, I thought, well, in order to actually get there, I think I have to learn more neuroscience. So I just decided to stop trying to advance the robotics, and then I jumped into neuroscience and ended up with a PhD in basically neuroscience, with the hope that by learning the human brain would allow us to advance the field of robotics. Certainly, there are a lot of things that I've learned, but by the time I studied neuroscience, I was captivated by the field of neuroscience. I've learned that there are something like 6 million stroke patients, or the stroke victims, that are out there who could probably use technology to live better lives. There are many different diseases, spinal cord injuries, Alzheimer's disease, Parkinson's disease. There are a lot of different neurological disease that there are ways that robotic device could improve lives. And then I kept thinking maybe there are ways that I can combine the neuroscience and robotics to help those people. And that was really the birth of the terminology neurobotics. I've combined the word neuroscience and robotics, so neurobotics. And I work on Ro. That's really what I'm interested in. And in this neurobotics, the moment I say the word neurobotics, many people imagine this one on the left-hand side, which you might imagine somebody who's missing arms, amputated, or legs, and have robotic limb replace their body parts and have their brain control that movement somehow naturally. That's what people immediately say the moment I say the word neurobotics. However, I also want you to sort of look at the other side, on the right-hand side, which shows the robot is a stationary robot sitting on the ground, and a person can just go up and sit in front of it. The moment it reaches and touches it, the communication of the neural system and the robot start. So the robot that's stationary and sitting, as the person is moving it around, can gather non-invasively some of the neural signals. And then the robot can act accordingly and then provide different forces and inputs to the person, and the person react to it and so forth. So it still achieves a closed loop feedback between the neural system and the robots. And that's still neurobotics. And then you can use devices like that to do stroke rehabilitation. You don't have to have missing limbs. We can actually train your brain better by sitting in front of robots. And that's part of neurobotics also. Specifically for my case, I'm interested in neurobotics from the point of view of human movement. We can combine it in the neural system and devices in such a way, for example, cochlear implants. That's also a system where you interface the neural system with some technology. But I'm most interested in how we can augment motion. So after stroke, some people might be paralyzed. Can we somehow retrain their motion? Or spinal cord patients who are paralyzed from their neck down, can we get them to move better again? So those are the level of things that I'm interested in the field of neurobotics. I wanted to give you a little anatomy course. So this is a 1-minute anatomy course of how the human information flows from the brain. When you think and says, I'm a little bit thirsty, that thought is in the electric current. So that's a parentheses I. And that current flows down to your spinal cord. That's the little tail of your brain. And that information flows onto the spinal cord. That goes out of the spinal cord in the nerve, still all in the electricity, in the current. Then it reaches the muscles. And finally, that's what the current gets converted into force, positional displacement, and stiffness changes. And those muscle contractions of those changes propagate to joints, joints move, and then affect the task and behavior in the external world. Then, those behavior allows us to sense things. We have skin, we move the joints, and we end up touching something. And those signals go back to the spinal cord, and that's actually a shorter loop than going all the way back to the brain. It's called a reflex. So if I touch something really hot and then jump back out, that doesn't require your brain. It's a much faster loop to prevent you from burning yourself too much. And also, I should tell you even the time scale. To go back to the spinal cord in terms of the it's hot information and executing that release back, that takes about 80 milliseconds. If the information went back all the way to the brain and thought about how to do it and came back out, it's about 250 milliseconds. So we're running at about 4 hertz. OK. Now, let me give you a 1-minute robotic lesson. So for robots, turns out it's quite similar. Computer is dealing with current and propagates through wires. Instead of muscles, we use motors, and that turns the current into torques and joint angles and stiffness changes. They often move metal joints and affects the rest of the world. So that is pretty similar in the robotic structure. And this is the reason why we can talk about body parts replacement or even some of the brain function with the robotic-like structure. So we can take different parts and replace them. So for example, let's now talk about some loss function augmentation. So some people are lucky enough to only lose a limb, but not lose some of the neural functions, such as this. So you volunteer to go to the war, and then, of course, with the recent medical advancement, turns out more people stay alive in places like wars, but they come back paralyzed, and then they live long life forever, not forever, but permanent with permanent disability for a long time. So there are a lot of people like this, a lot more than before. So brain is intact, all the spinal cord nerve is coming out, wanting to go to place, but no limbs to control and more muscles to control. In that case, as I've shown you, we can place a robot, and that's the picture that you've seen here. These are from RIC, the Rehabilitation Institute of Chicago. This is a technology called a nerve reinnervation. Nerve reinnervation allows surgeons to go in, find the nerves that used to go to the arm that's no longer there, and then re-innervate it onto the muscles that are still there working, in this case, pectoral muscle that controls the chest. And they rewire it. So now, as they think about moving the original hand or arm, the chest muscle ends up twitching because the nerves that used to go and twitch the arm muscles are now rerouted to twitch the chest muscle. Then they just simply go in and get those signals from outside, so nothing invasive into the skin, and then that's connected to the robotic device. So this technology, there are about 22 people in the world who have such system implemented on their body. Majority of them have arms and hands. And I think there are 2 people who who are implemented for the legs. So they're making advancements, and this is actually only happening within the last 3 to 5 years. I can show you as poster child Jesse Sullivan. He was the first guy. If you search bionic man on the Google, he's the first one who comes up. So he is just thinking about moving his original elbow, and he's able to move them now. So it's a really young field. As I said, there are only like 22 people who had this experiment and still being trained. He's been training with this arm for about 4 years now. But he's gotten to a point where he can move multiple joints at the same time to reach for an object, but he still has some issues with the coupling of the elbow movement and the hand grasp, for example. So as he tried to close the elbow, his hands also ends up closing. So that's one of the things that he's still training 4 years after he had this system embedded. So there are still limitations in terms of that level of resolution. Also, this technology does not work if the injury happened any higher than missing limbs. So what do I mean by that? So instead of being able to replace just the limb, assume that maybe you had a spinal cord injury, so you have a healthy brain, but there's no way to communicate that information to your paralyzed limbs. Maybe you're not missing limbs, so maybe we build a wearable robot instead, and then trying to find a way to get the signal from the brain over to control this robotic device. And we just do that through some computer device. So now, how do we actually get the signal out from the brain and then get it to the computer and control the robotic device? This is state-of-the-art from the company called Cyberkinetics, very young company. And they are able to put a chip into human brains and then get the signals. They've had 2 patient studies so far, 1 successful, 1 not. And they're no longer pursuing it at this very moment because the second patient was very unsuccessful. He's okay, he's alive, just that he really had a lot of pain. So this is how the technology looks like. This video is courtesy of Cyberkinetics. So embed a chip that actually has little electrodes that stick right into the tissue of the brain. Wire come out directly from a port and then onto the outside of the skull and then go through the port and can go into the computer. And specifically what they developed was by thinking about moving a cursor left and right and up and down, he was able to control the cursor on the computer screen. And if we could do this for people who have completely lost movement of their body, to the point that they cannot even communicate with people. There are people like that out there who can't even blink voluntarily to communicate. And so for those people, this technology is great. If we put maybe yes and no on the computer screen and ask them, are you in pain? And if you could actually think to move the cursor on a yes or no, then they're now able to actually communicate something to people. That's critical, and that's a life-threatening thing if they couldn't communicate how much pain they might be in. So the risk that currently, because there's a high risk in implanting something like that, which could cause massive infection in the brain, the amount that they really end up helping, for example, in this case, somebody who absolutely cannot communicate how much pain he might be in, it's worth that risk of the infection to actually implant something like this. But with 2008, October, as of today, that's about the level of aggressiveness that we can go into. So given if they have no way to communicate, but we really need to know what kind of things they're thinking about from the yes-no level, then we would go in and implant. And then there were 2 people like that so far who we were approved to experiment. So since we can't do it so much on people, scientists, what do? Well, we work with monkeys. So there's a collaborator from my collaborator from University of Pittsburgh named Dr. Andy Schwartz. He's very famous for working with monkeys and using their brain signals to control robotic arms. So this monkey was trained to move his arm towards wherever the food was provided. And during that time, the monkey's brain signal was recorded. So then the scientists found correlation related to where the food was presented and how the movement was executed and the brain signals. once that correlation was found, his arm was underneath the sheets, and then as he's thinking about the food presented and wanting to reach for that with his own arm, now that signal was used to control this robotic device. So now he is thinking about moving his arm to go for the food. That signal is controlling this robotic device, and he can deliver it back to his mouth. Okay, so this is really the state of the art of how much brain signals that we understand. It's to the point that we can decode about the XYZ location of the endpoint of the arm. The open and closing of the hand is actually something that we still can't get from the brain, so there's a graduate student sitting here with a remote control and opening and closing the hand at an appropriate time. But, this is pretty good, so there's some progress made. But again, I want you to sort of pay attention to this hand. I keep coming back to this human level dexterity. So for the monkey brain signal, we couldn't quite get this open and close signals, though many scientists are working on it. Another thing about that is in the hardware also. So going back to the human subject who had the nerve innervation, they were giving prosthetic hands, which to a certain extent look a lot like our hand, but it only open and close 1 degree of freedom. And after, those people are actually getting paid to wear this arm and train for 3 hours a day. And after the training, they immediately remove this arm and then put back their hook. They claim that that's more dexterous. They are able to function better with the hook still, even after 4 years of training with this device with the open and closed hand. Why? We don't know yet. And that's really what I'm after. I want to give those people the dexterity that they have. And it might be in the hardware. If we can provide better hardware, and if we can get more of the brain signal back into the system, then maybe we can now start to provide the human level dexterity back. Here are some prosthetics that also became available within the last about 3 to 5 years. So these are actually commercially available prosthetic hands. They cost about like buying a Lexus. So they all provide about 1 degree of freedom. The bottom left one is about buying a 2 Lexus and gives you individual finger control. And that just came out last year. So those state-of-the-art ones are very nice. And as I said, we've been making great progress in the last 5 years. But we're still somehow way behind in providing this human-level dexterity. We keep claiming that we're not monkeys and we built the society and buildings and all of that because of our hand dexterity. Some people even say the opposing thumb has allowed us to do all of this. Yet, when people get injured, we're not providing those function back. So we're getting them to be like monkeys. That's no good. And then on top of that, even if we can somehow understand and provide that dexterity in the hardware, we still also don't know exactly how to get that control signal from the brain to control that, provide the dexterity. So that's the state of the art in terms of the prosthetics. But in the field of robotics, where we're not as limited in terms of the size of it, maybe for prosthetics, we have to provide something light enough that people can carry and wear around. But in the field of robotics, it's research. We could actually have a big refrigerator behind it, and then as long as the hand is able to do dexterous tasks, maybe that's some achievement. So, can the field of robotics currently now achieve this dexterity? That might not be wearable for people yet. So here are the robotic hands that's been in research for the last 25 years. Starting from the top left, really 25 years ago, 1983, that was the first publication of dexterous hand called the UwMIT hand. And it had 5 fingers, had all the same joint movement as human hand. And pretty much the difference between that hand on the top right versus the top left and on the bottom right, which are newer hands, is in the size of the controller. So for the UwMIT hand, the controller was about the size of 2 refrigerators. And now with the cyber hand, the controller can fit into about the size of the forearm. Besides that, the hand hardware itself hasn't changed very much. They all have, as I said, sort of approximately the right number of fingers as we have them. But somehow, whenever engineers get together and say, oh, let's go and build a robotic hand, there are certain ingredients that always go into it and certain ingredients that always get forgotten. For example, if you look at the Gifu hand on the bottom, close to the right, you can really see prominently the palm. Somehow, every time roboticists think about building a robotic hand, they build a rigid palm. It's a convenient place to put a lot of electronics and motors and cables and so forth. So immediately, nobody even think about making anything flexible, but make a rigid palm. But imagine if your hand had a rigid palm and trying to grab anything, right? It's really, really hard to do. And turns out we use our flexible palm all the time. But roboticists, and I'm going to criticize myself because this is my field, but roboticists, we just haven't figured out that that is an important function to include or something that must be included as we move forward for the field of prosthetics. And utilizing those hands, so far in terms of the control of the robotic system, I will show you two examples. One example looks a lot like human on the left, which is a Toyota humanoid robot, but is completely controlled pre-programmed. And then the one on the right-hand side is a very fast pen twisting motion, which is not human-like at all. So the one on the left, again, the violin playing robot, it looks really impressive, but it's completely pre-programmed. If I went and then pushed him a little bit, he will still keep doing this thing on his own. Even the violin might have fallen over. He would have no clue about that. Even from the controls point of view, it seems that the robotic hand has not achieved the human level dexterity for some reason. So why no human dexterity is really what our group has been addressing. But hardware, it seems that many of those joints don't really move in a human-like way. And as I said, the palm is a really good example where, it just doesn't move in a human-like way in all the robotic devices out there so far. But another problem is that we don't really know exactly which salient points from the biological system we ought to be mimicking in hardware. So, okay, palm, that's one thing I clearly pointed out, but thumb apparently has this passive little degree of freedom. If you lift something very heavy, your thumb actually rolls over. It doesn't actually stay rigid. Are those features important? Should we really be mimicking that? Maybe we want to mimic that. But then, we keep going further and further, and not sure where to stop or which one to not include. So that's something that we don't know yet, how much to go. Another thing is the software. We also don't know, given if we really could provide you a robotic device that acted or had all the biomechanical function like this one, do we know how to control it? Well, we don't know the answer because we've never had such as hardware anyway, but maybe we actually need to know a little bit more about the human brain signals so that we can implement this artificial intelligence signal to do so. So those are the things that we've been after in terms of pursuing human level dexterity. Our approach is to really understand the human musculoskeletal details. So that's biomechanics of the hand. Then, once understand the hardware, try to understand the neural control of movement of the hand that would enable the human level dexterity, and finally using those to augment injuries. That's really our philosophy. And our philosophy has been executed by generous funding and lots of people. And in 2001, we have built our first prototype of what's called anatomically correct testbed. Because we weren't sure exactly which feature we wanted to mimic, rather than sort of keep including one feature at a time, we went all the way to the beginning and said, you know what, let's mimic whatever we can mimic. And let's find out maybe certain things that we didn't have to mimic, and we'll start dropping them. So that was the philosophy that we used. We got together with hand surgeons and animatronicists. It's a fancy title for people who build dinosaurs for Hollywood. And we came up with this great robotic hand. And we built this thing in about 3 months, and it played keyboard in a museum for about 6 weeks without failing, 9 to 4. And that was impressive. However, by the end of 4 weeks, it got much harder to control, and we couldn't figure out why. So we asked the hand surgeon, said, do you see anything that's sort of wrong with this hand? And he tested a little bit and said, I know exactly what it is. This hand has developed arthritis. So without all the cell replacement, turns out the joints get tired, they rub, and then get painful. And that's exactly what happened. Now we still have this hand in our lab. If you ever come and visit, the joints are really, really stiff. But we learned a lot by building this hand and running it for a long time. There are certain things that we can mimic right away with the material science that we have, and there are things that maybe we should not be mimicking exactly yet. So from that point on, we've iterated and iterated and iterated for 5 years until we could get what we were happy with. And now, this is what we have sitting in our lab. We're quite happy with the amount of biological features that we've mimicked. And if we could do more, we would love to. But for example, joint structures, we had to go with fairly traditional, creative, but fairly traditional gimbal designs for different joints. But for this finger, or for this hand, we can show you the motion. The finger itself is a previous version, so it has metallic bones. But the motion is driven by the human finger moving. We can track the human motion, and then we can execute it in this form. If you can tell, this robotic motion is quite human-like, very dexterous. So if we can imagine having multiple of these fingers together, we can do dexterous motion. That's really what we're after. We can also take the muscle signals that are moving that human finger and implement it or export it onto the robotic finger to make the robotic finger move. So to get there, we made a few different discoveries. And so far, the discoveries has been in the area of biomechanics and neurosignal choice. And I'll tell you a little bit about that in the next about 5 slides or so. So one of the interesting things about human hand is that it has complicated web of tendons. If we peel off your skin, I don't recommend you to do this at home, but if we peeled off your skin, we have lots of complicated web of tendons running on every finger. And if we modeled it, it will look like the one on the top left, where there's connections everywhere, and then those tendons are interconnected with each other. We thought, boy, we don't want to mimic this if we could avoid it. So we tried different iterations of that. And turns out, we wanted to ask the question of, is this an evolutionary marvel or baggage? I was going to say garbage, but it's baggage. It would be really nice to find out. It's something that we've evolved to utilize very well, so therefore we must have it. Or if we can cut some of those parts off, or replace it with something simpler, that would be really nice from the engineering point of view. But so far, to date, we found every connection to be extremely useful, and turns out that the index finger motion if we build this in a robotic form, would require 8 muscles, but humans do this with 6 muscles because of this complex web of tendons. So that part seems to be something we want to keep. Okay. And because of this complex web of tendons that make some of the muscles to have dual roles, now starting from the same configuration, you can end up in the bottom left or bottom right configuration utilizing exactly the same muscle activations but in different orders. So the timing of how you activate the muscles turned out to matter a lot. And the moment that we decided that we really want to keep those tendons, the shape of the bones turned to matter because the tendons glide over the bones. The bones are used like a moment arms. And when we had those cylindrical bones like the one on the left, the tendons didn't work as well. And that we really wish that we didn't make that discovery because making those groovy, bumpy, nonlinear bones is really, really hard to do. So we have to scan the human bones and then convert that into some format that the SolidWorks or Pro-E models can take and then use the right materials to print it. Whew. But we've done it. It took many, many years to do it. So, but we were glad we did it. So after we did all those bumps and grooves together, and then we analyzed the input to output relationship. So if we actually pull the muscles in a certain way or activate the muscles in a certain way, what effect does it have on the finger motion or the strength? We found out that because of the bone structure and the shape that we have, we are naturally strongest in holding object direction. So take the index finger, and if you are flexing, so curling your finger down and moving it towards the center of your hand, you are strongest in moving in that direction because of your bone structure. So for any given level of muscle activation, you're strongest in this direction over other directions. You can think of it also in the other way around. If the muscle was activated in the maximum sense, we'll go the other way around. So evolutionary speaking, you also would be able to hold on to an object strongest and longest in that direction, towards the center and curling direction. Kind of makes sense. Maybe we evolved over time that we had to hold on to an object for a long time. We wanted to do it in the most efficient way, and that's exactly what the bone shape accommodates. And we just recently found that out in 2008. One more thing. We've been not only looking at biomechanics, but of course we want to connect this complicated biomechanics system onto the neural signal. We believe that if we mimic a lot of the nonlinear system in the hardware, we'll be able to utilize the natural neural signal to control this system to still express the dexterity. So a couple of things that we found. Actually, there are 3 figures, and sorry, that's a little bit crowded. This is appealing more for geeky type people. So the one on the top right shows 2 green blobs. What I want to convey is that for you to produce force with your finger, let's take index finger as an example. You're actually doing this with 6 muscles that you have, and then you have 4 different joints or degrees of freedom. So you have 3 joints, and the knuckle has up and down and side to side, has 4 degrees of freedom. To do this, turns out we have infinitely many different ways to do this from our brain. So to move finger up and down, I could actually do this in a relaxed way, or I can do this in a really tense way. Now I'm doing it really tense. Okay, all right? So, but from the emotion expression side, now I'm relaxed. So from those 2, they look the same. Most of the output is the same, yet my brain just produced 2 entirely different ways of doing it. And turns out even within the tense mode like this, there are even many infinitely different ways to do this exactly same tense way to do it. So we actually then found out that the top right figure shows that the possible range of neural signal, I guess the redundant space, so we call it, the size of that is bigger if you're producing smaller level of force than big level of force. Meaning that if you produce highest level of force pushing onto something, there's only eventually one way to do it. But if you're putting relaxing amount of force, you can do this in many, many different ways. Kind of makes sense, right? You're pushing really hard, and if I said, okay, now do this in tense way or relaxed way, you can't really change very much. But if you're producing much less force, I can do it in multiple different versions. We found that out in a mathematical way. And we also found that we can use a technique called manifold learning to spread that space into and blast it onto a 2D printable format, because we can just think in a 6-dimensional way in our brain all the time. So once we blasted it, now this green blob shows all possible neural signal that would produce the same output. Okay? And what we wanted to know, scientifically speaking, was that if many different neural signals produce the same behavior, do we actually care which neural signal that we use? Maybe we don't care which signal we use. If we recorded it every time we did something, maybe we're using dramatically different brain signals every time, as long as the output is the same. So if that's the case, within the green blob, all the recorded signal would be everywhere in this green blob. So that's what this green blob represents. Anything inside would produce the same behavior. But as we recorded it, we found out that humans actually use, even within many different neural signals that you can use to come up with one behavior, people still use some clustering methods within that. That indicated to us that we seem to use another level of optimization in the neural system to control our movement. And such optimization, we thought, well, maybe what we care about might be energy minimization. Engineers, we like this thing called minimum L2 norm. And we thought, maybe we're trying to simply minimize the energy expenditure and see if we can calculate to see if we minimize the energy, we would come up with the same biological solution. We calculated that. Turns out it doesn't match up very well with the biological signal. After trying a variety of optimization strategies, we found out one way that matches up really nicely with our biological data was to maximize the utilization of small muscles, but then minimize the utilization of big muscles. Our hand actually has small muscles packed into our palm and big muscles packed into the forearm to do this. Turns out, when we're doing precise tasks, we're maximizing the utilization of small muscles and trying to relax those big muscles as much as possible. We don't know what that means yet, but at least that's what we found to match up to the biological signal that we found. It doesn't seem great from the ergonomics point of view. Maybe, if you are in the field of ergonomics, you might tell people to use bigger muscles and then not strain some of the smaller muscles. However, that's not what we seem to do. And we're trying to find out why that is right now. And we're also working now up the stream with neurosurgeon Dr. Ojiman from the University of Washington. He is an epilepsy neurosurgeon. He puts on sensor grid on people who have seizures to isolate and locate the location of seizure. But while they have the sensor grid on and waiting in a hospital bed when they have the seizure, they have this brain signals porting out onto the computer 24 hours a day. And so we go in and then get patients to perform some hand tasks. And then we look at the correlation of the brain signals and see if we can understand more about that. OK. So that was sort of took you into this narrow path of prosthetics and brain-machine interface and hand-controlled dexterity, robotic control biomechanics, and neural optimization. But the field of neurobotics is much bigger than that. And even within my lab, it's bigger than that. We work on that, starting from the top left. That's what we described about an anatomical model and the prosthetics and brain-machine interface. We're going to go clockwise. We talked about exoskeleton. So for people who don't have to have limb replaced, but they have their original limbs, but they can't control them, we'd rather be building wearable robotic device. One day will not look clumsy like that, but maybe like a little suit that they zip on and wear. That is controlled in a similar way as a prosthetic device. On the bottom part, we also do quite a lot of robotic rehabilitation for stroke, cerebral palsy, spinal cord people utilizing stationary robotic device. And we work on ideas of manipulating some of the feedback people get and then how to gather some neural information as they interact with the robotic device. And interesting enough, the field of neurobotics has an impact on a lot of areas. Starting from the top left, now we're going to go counterclockwise a little bit. First few are obvious that we make scientific discoveries. We affect the field of rehabilitation and assistive technology. But what we do, we can also utilize it for disease prevention or prediction. Turns out, maybe in the mid-1990s, some scientists from Johns Hopkins have found that if we couple people to a robotic device and a robotic device detects some of the neural signals, they were able to detect the onset of a disease called Huntington disease up to 7 years prior to the clinical onset detection. This is purely by the ability of robots to just detect subtle tremor, motion difference, and how people accelerate and decelerate the motion. So it's pretty interesting to think in that way, that we can probably start utilizing devices as a way to have checkups. You go in the hospital, you play little video games with a robotic device, and at the end they tell you and says, you seem to be all right. Or saying, well, maybe you're under risk for Parkinson's disease. It might be creeping up. Here's a medication you might be able to take. That's interesting. We can of course, utilize this idea to sports training. Maybe I can finally loop back to tennis buddy. We'll see. As you saw, we have some ergonomics flavor, evolutionary biology flavor. We want to provide personal assistance, or robots moving around with a wheelchair, with a dexterous robot that can execute tasks for you. Space exploration, same idea. Telemanipulation. Now we can send those things up into space and then can turn over rocks and pick a little bug in Mars or whatever that they do with the dexterous hands. Computer graphics, the more we understand about the human system, the better simulation we can have, so those bugs' life, those bugs can walk around more human-like. And we really also are emphasizing the human technology interface. The more we make progress in the neural understanding, the better computers, mouse, keyboards, iPhone, anything that you might be able to interface will be designed better. So the field of neurobotics has many different impacts in different areas. And the field of neurobotics is only a subset of the area called neuroengineering. Neuroengineering is basically the idea of putting all the engineering fields and science areas together to uncover more about how the human brain works or to restore lost sensory motor function. And turns out, Seattle, this area, has lots of scientists who care about and work on neuroengineering. We just actually hosted a workshop in this area by emailing a bunch of people who seem to like their webpage says that they work on neuroengineering. We were able to actually get about 100, actually we had 151 registrants. Out of those, about 120 of them are at the MD or PhD level who are doing neuroengineering research. So we are trying to put all those people together and make this the place to be. So now people who want to do neuroengineering, students, professors, researchers, would come here because we have the best program. We also want to get to a point where industries can't help but to come to Seattle because they know that's the place to be, the buzz is there, and then they will lose their brand name if they weren't here. That happened for Silicon Valley, right? So all those companies had to go there, and we wanted that to happen for Seattle. That's great for our Pacific Northwest economy. Our house price would stay high, all the important things. Okay, so we're doing this for you. But I just also wanted to tell you that I am also very interested in doing things that's not sort of in the research area. I've been looking at more of a 20, 30 years down the road and trying to see if I can affect things in a, providing dexterity. We're not talking about 5 years from now people be walking around with a device that does this. But, that's my research. But I also want to affect people now in some way, and that's how I do my outreach activities. So one of the ways I use neurobotics is to come up with ways to couple engineering students and some minority students, women students, high school, junior high students, to work with disabled kids. We pair them up and then come up with something fun to work on. And specifically what I've done so far was to ask them, or ask the disabled kids and say, if the Santa Claus was an engineer, what would you want them to bring this Christmas? And they make up a list, and about 8 of them are impossible to do. And then, but the 2 that we might be able to work on, we give them to some students to work on, and then we provide them. Some ended up being so productive that ended up in journal publications done by high school and college, the undergraduate students. A great example here was that hand exoskeleton device an undergraduate student had built that allowed the paralyzed stroke a spinal cord patient to be able to grab objects, soft or hard. He had a device that allowed him to grab objects in a certain constant force, but he said that he couldn't eat Twinkies. He said Twinkies always crushed all the way, and he was very frustrated with it. So our device now allowed him to grab some soft object. He loved it. So, those are the kind of things that we do. And also, those are sort of the full quadrants of things that I'm personally interested in terms of doing things now. So starting from the top left, I want to provide robotic assistance now. There are things that we can already do. I'm interested in recruiting girls, minority, and disabled students to enter our field because we need their opinions. We currently have fairly male-dominant field, and that needs to change. I'm also very interested in, at the bottom left, assisting women who are in the workforce. Turns out it's really, really hard to do this. Working and managing to have kids, and then I'm sorry, this is a cheap way to put my family picture in for this talk. But so this is really hard to do, and then even childcare options, those things are really hard to do. And now I understand what it is that it's hard, and I want to help. But there's another side to this, turns out, that there are a lot of extremely talented women who decided that they're going to give up and pursue mommyhood. And that's also turned out to be hard because they're now looking for something meaningful to do with their lives, maybe a little bit more than PTA work. And finally, I'm interested in lifelong learning and opportunities. As everybody, all of us are unfortunately getting older, we want to keep learning, and I'm glad you're here, and have more opportunities and environment to provide that. I have about 2 company startup ideas that kind of encompass in all those 4 fields. So if you are interested in any of those fields, I'm happy to talk to you about that. So that concludes my talk. Here is the webpage for my lab and myself. And then if you want to learn more about that, please visit and send me an email. Thank you very much.